Going to do a quick introduction to mechanical properties. There are a lot of mechanical properties out there, and I know that's something that's really interesting to a lot of engineering students. There are lots of things that we can go over. There are other classes that go into some of the testing. Really what we're going to do here is we are just going to kind of do an overview of these. We're going to start off by talking about normal stress and normal strain. These are stresses and strains due to a force that's applied normal to the cross-sectional area of our material. All right, so what is a stress in general? A stress in general is an internal force that are induced by deformation. So the key points here is that it is internal, and it is caused by the fact that we've deformed our material. There are different types of stresses. We already talked about what normal stress is. Even within normal stress, there are other types. The one that we use the most often is engineering normal stress. And this is the equation for it. We have stress here, and stress equals our force over our original cross-sectional area. That's what A naught is. That's our original cross-sectional area. As we deform our material, our cross-sectional area will change, but it makes it much easier to run these tests if we just use our beginning area. Our strain is the deformation of a material due to an external force. And so again, it's deformation. We're deforming a material, but the reason it deforms is because of something that's happening externally. Again, we have engineering normal strain, and our engineering normal strain is equal to our change in length that happens as we deform over our original length. All right, so I wanted to kind of get a picture here. Let me shrink this down just a bit. So this is going to be what it looks like on the macro scale, what we see as we test our sample. We're going to get these specimens, and we can water jet these out. We can machine them. There are different ways that we can get a specimen, but what we're going to do is we're going to get some material. A lot of times they're metals, so something, let's say, like aluminum or steel or copper or brass or something like that. And I tried to draw this out kind of in a three-dimensional have a three-dimensional look to it. I wanted to label a few things on here. So this is a tensile test. What a tensile test means is we put this thing in tension. We put this in and we pull it apart. And so what I'm going to do is I'm going to clamp onto these. We get these jaws and they clamp onto the ends here, the fat ends here, and we're going to clamp onto it and we're going to start pulling. What we're going to do is we're going to use these equations up above to get our stresses and our strains. So we have this force, that's what we're pulling our sample with, and we're going to divide that by our original cross-sectional area. So our cross-sectional area, we're just going to find some spot where we're going to be doing this stretching. And this here is our A naught. Now, for the most part, most of the stretching is going to occur over what we call the gauge length. It's the skinnier portion of the sample. The reason why we shape this sample, the specimen, this way is because we have these big ends that we can kind of clamp onto, a little bit more material to grab onto, but also what we want to do is we want to kind of force the material to deform over a particular region or a particular volume. And the particular region that we want it to stretch over is going to be what we call the gauge length, somewhere in between here. What we can do is we can say, all right, we can take a measurement before our test, and we can say that is our L naught. That's our original length. So before I start the test, I need to take a cross-sectional area. I need to get my original length. And from there on, during the test, I can apply different forces. So I can calculate my engineering normal stress at any point, depending on the force that I'm applying. And I can also calculate my engineering normal strain. And all I have to do there is I see what my difference in length is throughout my test, and I divide that by my original length. And so what we see here is as I continue to pull on our specimen here, we have a length that has changed. It's gotten larger. So this is just any specific L throughout our test. And what we could say is this is going to be L naught plus some change in L. We have our original length plus whatever length we'd added onto it throughout our test. The other thing that happens, though, is our area gets smaller. This is no longer our original area. As we've stretched this out, we have conservation of volume, let's say, conservation of mass. They have to have the same amount of material inside of this gauge length here. And if we get a longer, if it gets longer in one dimension, then it has to get smaller in some other directions to make up for that. That's a little bit complicated to do, to take measurements throughout and keep checking that that area throughout our test. And so that's one reason why we like to use what's called engineering stress and engineering strain, because we can just use original values. We can talk about our original area, our original length, and we can still calculate things. There is the possibility of having what we call true stress and true strain, where we take into account the area changing throughout the process and taking into account very, very small changes of our change in length rather than just one big change in length throughout our process here. What I want to do, though, is I want to say, all right, this is what we're seeing. This is the macro scale, but why don't we try to figure out what's happening on the micro scale? So when we first start pulling on our sample, we have all these atoms inside of our material, and they're all lined up. They're in our crystal structure. And they don't want to come apart because they're attached by bonds. And these bonds, a lot of times we say that bonds are like springs. And so as I go ahead and I pull this apart, just like if I were to pull a spring, what's going to happen as I stretch this is these springs are just going to stretch out. And that's exactly what happens at the beginning of our test here. The beginning of our test, we can model it just like we would a spring. And so what we can do is we can model this beginning part of our test like a spring, which would be using Hooke's law. I am getting a little bit ahead of myself here. I want to talk about a few things really quickly. I'm going to shrink this back down, or sorry, I'm going to zoom in a little bit more. We'll probably go back up to those pictures a couple times to discuss some things. But if we wanted to plot a stress and strain so that we can get a relationship between these two things, the question would be which one would go on the x-axis. So if I plot anything, we have our x-axis and our y-axis. Our x-axis is the thing that we can control. Our y-axis is the thing that happens because of that. The question here is which one of these is going to go on the x-axis, which one's independent. Now, technically, the independent thing is the external force. It's the thing that we can apply to our material to deform it. But what we're going to do is we're going to kind of skip that step, and we're going to say, all right, we're going to put on our x-axis how much our material has strained or how much we have deformed it. Granted, we had to apply some force to do that. We're really saying we're controlling that deformation by the force that we apply. So on our x-axis, we have our strain. And what happens when we strain our material? By definition, we get internal forces that we call stresses. So remember, if we come back up here, our strain is our deformation due to an external force, so that's something we can control. And the thing that's going to happen when it deforms is we're going to get internal forces. We kind of already talked about gauge length and the cross-sectional area. Talked a little bit about true stress and true strain, how those take into account a changing length, very, very infinitesimally small change in lengths, and a changing cross-sectional area. And we got to the point where as a specimen is pulled, the first thing that happens is the bonds stretch, and that this acts like a spring, acts like Hooke's law, and therefore is linear. So in this region, in this linear region where all that's happening is we're having these stretched springs, these stretched bonds, the length will change. It will strain, and it's due to bond stretching only. And since we're doing nothing more than just stretching a spring, what happens when we take a force off of a spring? It goes back to its original shape. And so if I'm straining something in this linear region where bonds are just stretching, it is reversible. I'm going to keep stretching this though, let's say, and after I stretch it too much, it's not just going to keep stretching these bonds. At a certain point, I'm going to start breaking bonds. And when I break bonds, atoms will begin to move, planes will slip. We talked about imperfections in our material, and some of those were dislocations. Dislocations will move, they'll migrate through our grains. In other words, what's going to happen is as I keep pulling my material apart, as I keep straining my material, the microstructure is going to start changing. Once the microstructure changes, it's going to be no longer be reversible. Now I have this picture here, but I want to go through it one at a time. And so we're going to start here, where we have our strain on our x-axis, and that is going to be often measured in millimeter per millimeter. Remember, it's a change in length over original length. We could do inch over inch, or we could do what's called a microstrain. And microstrain is nothing more than taking into account whatever our millimeter over millimeter is, but doing 10 to the minus 6. In front of that, because a lot of times these are very, very small. So microstrain is just really measuring these really small amounts without having to deal with really, really small numbers. On the y-axis, we have our stress, and stress is measured in pressure units such as PSI or some type of Pascal. Normally not straight up Pascals because those are pretty small, but something closer to megapascals, maybe gigapascals, in some cases maybe kilopascals. But some type of pressure unit is going to be on the y-axis. We're going to get some type of curve, and it's going to look something like this. So we could test something, we could measure our strain and our stresses at any given point, and we might end up with a curve that looks something like this. What we want to do is we want to start dissecting this and trying to figure out what's going on. So we can easily see that at some point we're going to have, or I guess I should say in one region, we're going to have a linear relationship. That linear relationship, again, is when we're just stretching things, where bonds are just stretching because it acts like Hooke's law, which is linear. But at a certain point when I stretch it too much, it's not going to be linear anymore because things start changing. Instead of bonds just stretching, I have a different type of mechanism that's happening as I deform my material, and that's going to be, again, bonds breaking, planes moving, dislocations moving, atoms moving, and those types of things. So we have on one end here what we call the elastic region, which is reversible, and we have our plastic region, which is not reversible. In our elastic region, if we take the slope, and anytime you see something linear, you should instantaneously say, I want to know what that slope is, and try to interpret it to mean something. In the case of this elastic region, this slope, we call the Young's modulus, or the modulus of elasticity, and we use a capital E to denote that. And really that tells us what's happening with the material, how our stress and our strains are related while it is in this elastic area, this elastic region. When it transitions from elastic to plastic, we have a point, and in this point we call it the yield point. Yield can mean many things, and in this instance yield means to give into. It's going to, we've been applying some force to this material, and finally it's going to give in, and it's not just going to stretch, it's going to start permanently deforming, it's going to start plastically deforming, and that's our yield point. Once we get past our yield point, we get into what's called strain hardening. And strain hardening is going to be when we have inside of our material all this movement that's happening, and as things move, it's actually going to make the material harder. I'm adding energy as I pull my material apart, and as things move, this added energy is going to pile up the slip planes, the dislocations. It's going to move things around, and it's actually going to harden my material. It's going to strengthen my material slightly. But what we can also see is that we're actually getting an increase as well in our strain. So our material is deforming significantly sometimes in this region as well. We're going to reach a point, and the point where we're at our maximum is going to be called the ultimate tensile strength, or the UTS. This is going to be the maximum stress that our material can handle before it begins to fail. Once we get to this point, all of this strain hardening has hardened our material, it's strengthened our materials in some ways, but it's also started to make it so that our material wants to start to fail. As it strengthens some spots, it's going to weaken others, and those weakened spots are going to start becoming exploited, and we're going to get what's called necking. That's where one area on our specimen is really going to start to shrink down and break apart. At some point, we're going to fracture. Fracture and failure are slightly different. Failure can really be anywhere in any one of these regions. Necking is definitely a form of failure, but fracture is when the material has actually broken. Anytime we see a curve, we've all taken calculus, so anytime we see a curve, when we look at it, we should always assume that the area under the curve is something of importance. And this is no different. In our elastic region, the area under the curve is what we call the modulus of resilience. What that's going to say is it's going to tell us something about how resilient our material is to not permanently deform. Because remember, once we pass this gray dotted line, we're going to start permanently deforming. So everything to the left of this is going to tell us something about before we deform. Now it's important to understand what the units are here so that we know what the area under the curve is talking about. Remember, on our y-axis here, we have force-like units, but they come in the form of pressure. So we have force over an area, and then we have on the y-axis, or sorry, my x-axis, let me move my mouse so that goes away, we have length type units. They come in the form of a length over a length though. And so if I look at these and I combine these, what I actually end up with is a force times a length over an area times a length, which turns into an energy over a volume. And so what we're really getting in this area here is it's how much energy per unit volume my material can absorb before plastic deformation occurs. It's also interesting to note the entire area under the whole curve, which we call the modulus of toughness. Again, that's the energy that it takes to completely fracture my material. And I believe that is everything on this picture. This is something that there's a lot of information you can get from a simple test where you just measure what force you're applying to something and measuring how the length changes as you do it. You can really find out a lot of information on this material. And this is just kind of the beginning. We can figure out what this Young's modulus is. We can figure out what the yield point is. Sometimes there's different types of yield points, and we're going to talk about that in a moment. We can fit a line to the strain hardening region. We can figure out the maximum strength. We can figure out different energies that are needed to do different things. lots and lots of information can be used from a test like this. And so in class, we can discuss this a little bit more. But I kind of wanted to get into the yield point. So number one, how do we find this yield point? There's going to be three situations that we're going to talk about. And in the first situation, it's just we have a very distinct yield point. If I were to show this picture to you guys on a test or in class and say I want everybody to tell me where you think the yield point is, once you know what the yield point is, where we go from our linear region to our nonlinear region, I'm pretty sure that the majority of people would be able to pinpoint it exactly and say our yield point is right there. And I'm pretty sure that most people would agree with very little coaxing that that is our yield point. If we have an option like that, our yield point's very easy to find, then that is great. In reality, a lot of times we don't get something that looks that clean and neat. So another option is, don't want to scroll too far down. Another option is our upper and lower yield points. Sometimes we'll get something that looks maybe something like this, where I have a linear region. Whoops. We have this linear region, and then it goes into a nonlinear region, but then we decrease a little bit before we start increasing again. And so we could say, all right, well, where exactly is the yield point? The yield point in this one we actually are going to say is here, and it's here. We actually get two yield points. We have an upper yield point, and we have a lower yield point. Now, the materials that tend to do this the most are materials that have interstitial atoms in them, or they have substitutional atoms that are of significantly different size. And what I mean by that is we're going to have our lattice. And remember, an interstitial atom is an atom that sits between our lattice sites and often is significantly smaller than the atoms that are sitting at our lattice points. So as I start to stretch this material, as I start to pull this material apart, bonds are going to start to stretch, and at a certain point, we're going to stretch these bonds, and it's going to allow these interstitial atoms or smaller atoms within our material, it's going to allow them to start kind of moving around before the larger atoms start to move around. And so up until we get to the upper yield point, they are for the most part going to stay put. They're not going to move around at a high rate. But as soon as we get to this upper yield point, these smaller atoms are going to be able to move and migrate more quickly and more easily, which is when we get this drop. And when it starts to have a little bit more movement with our larger atoms, we're going to get this increase again in our stress and strain. And so this, again, normally happens only when I have materials that have these interstitial type atoms. Then we're going to get sometimes something that looks like this. And we actually get this picture quite a lot. And this is where things get somewhat difficult. If I were to ask everybody in this class, I want you guys to tell me exactly where the yield point is. I'm probably going to get some different answers. And the different answers could range significantly. A lot of people might choose somewhere in here, but maybe even a little bit larger area might be somewhere in here. That's not good when we're trying to talk about science. We want to be able to quickly and easily talk with other people and let them know what an important spot on this chart would be, this plot would be, such as a yield point. We don't just kind of want to say we have this region where it could possibly be at. You don't want to write a paper or read a paper or have some type of information on a material where we have this maybe somewhat large range that's somewhat ambiguous. And so if I do want to figure out a yield point for a material that looks like this, what we're going to do is we're going to use what's called an offset. And what we're going to do is we're going to mark some strain as our starting strain. And often this value here is 0.2%. Remember, strain is nothing more than a percentage anyways. It's a change in length over original length. Another way to write this would be a 0.002 strain. That is pretty common, but depending on the material, it could range from maybe as low as 0.1%, maybe even up to 5% for a material that's has a really non-linear section. But what we're going to do is we're going to find this point of strain, and I'm going to draw a parallel line to my linear region. So I'm going to figure out whatever my Young's modulus is, because that is my linear portion, and I'm going to draw a straight line with that same slope that goes through our 0.002 strain. What I'm going to do is I'm going to figure out where that linear line that I just drew crosses my data points. And I'm going to say that is going to be my yield point. Now, obviously, the material has started to yield before that. Otherwise, we would never be able to get an intersection, because if they were completely parallel together forever, then no yielding happened and we are completely just stretching bonds. But what we're going to do is we're going to try to find this spot that is close enough to follow our elastic region for a while, but not so far as to where we've really gotten into that strain hardening region over here. So we try to find this spot where we can mathematically determine where a yield point should be. And we do this so that there's no argument. Now, we can probably all take a step back and look at it and say that's not the true yield point as far as nature is concerned, as far as what's really happening inside the material. But what this does is it allows us to write a paper, to read a book, to be able to look at a material, and for everybody everywhere to be able to agree on a yield point. We say that this is our yield point with a 0.2% offset. If somebody were to use a 0.1% offset, we could say, all right, this is our yield point with a 0.1% offset, or a 0.5% offset, or a 1% offset. But what it does is it mathematically makes it so that we have some correlation, and it makes it so that we're not going to just sit down and pick random arbitrary points. I did want to talk quickly about what's happening in this necking region. I had a nice picture drawn up and I forgot to copy it over, so now you're going to have to deal with my crappy drawing. But what happens in this necking region is as we're pulling our material apart, and we get the strain hardening, we get things moving around. I have this grain structure inside of here, and dislocations are moving, and atoms are moving, migration's happening, planes are slipping, all kind of stuff is happening, which is making it so the material gets stronger. Things are piling up with these grain boundaries, making the material harder. It's putting concentrated strains, stresses at different parts of my material, which actually hardens it. But as it does that, it's actually leaving and coalescing some voids elsewhere in my material. I can't move a bunch of a bunch of dislocations and planes and atoms and have them kind of pile up somewhere without leaving something else out. So at this ultimate tensile strength, we kind of have this balance where we have a lot of spots in here that have a lot of stresses in them, but we also have some spots in here that are beginning to weaken. And once I begin pulling on it a little bit more, it's going to find a weak point. And this is kind of the idea of a chain is only as strong as its weakest link. It's going to find the weakest point at this right now, and let's say that point is right here. What's going to happen is up until this entire point, my entire length has been stretching mostly uniformly. But after it starts to neck, the majority of my specimen stops stretching. It'll stay stretched to where it's at, but it won't stretch anymore. Because what happens is at this point, it starts to neck, and that's a really bad drawing. I like to think about this as if you've ever had any type of kind of like a sticky candy, such as a caramel or a taffy, or if you've played with silly putty or something like that. As you pull on it, it originally starts out maybe as a square shape or a rectangle shape, but as you pull on it, the middle is going to kind of start stringing together where we kind of get this wispy part in the middle. And that's what we call necking. And at this point, up until this plastic region, like I said, the whole material is stretching mostly uniformly, but after this point, we're now measuring something different. The length change, instead of being across the entire gauge length, is really just the change in length that is happening over this necking region now. And so that is something important to note. It's also important to kind of know what necking is in general. And I just want to mention that before we moved on. Now comes the real fun part. We got to talk about it though. And that is we're going to go over some definitions. A lot of these we've already gone over, so we'll touch on them pretty quickly, I'm hoping. We can talk about them more in class as usual. First, I'm going to talk about strength. And strength is the ability to withstand an applied load. When I apply a load, my material deforms, and it's going to have some amount of stress inside the material. So the amount of stress that it can withstand would be maybe another way to look at strength. And that's why, let me scroll up again real quick. This point right up here, the ultimate tensile strength, it's the ultimate strength that a material can withstand when it's in tension. And that is, again, going to be the maximum stress that we can put on our material. We have two of those we've talked about. We have the yield strength, the stress at which minimal plastic deformation occurs. The ultimate tensile strength, the max stress a material can take. We have failure, which is a material's functionality has been compromised, or failure is when a material's functionality has been compromised. So it kind of depends on what the point of the material is. But in general, when a material starts to neck, it's a form of failure where deformation happens at a point. And we just kind of talked about that. Fracture is definitely failure. It's when a material has broken apart. It's fractured. Yield is when we begin plastic deformation. We've talked about elastic and plastic. Toughness. I really want to talk about these next few, though, pretty closely. Toughness. It's the ability to absorb energy. I think I will go ahead and move these down. I want to draw a couple pictures for these. So toughness is the ability to absorb energy. And remember, energy is the area under the curve. So let's draw a quick picture. A stress strain curve. If I want a tough material, I want as much area as possible. I would want something, let's say, that looks like this. And I have this pretty big area underneath my curve. That's a pretty tough material. But this is just kind of the generic picture of the curve. Not all of my curves look like this. There are some materials that would look something like this. Very, very steep Young's modulus, very, very steep slope here, very, very high strength. But just because it's high strength doesn't mean it's tough. It doesn't necessarily absorb a lot of energy because, again, I'd be looking at the area under the curve. If I had a material that looked like this, but it went out really, really far, this material here, this last one that I drew, the one in blue, would not be as strong as either of these other two, right? Because the other two can withstand a higher load. But this one it strains a whole lot. It can absorb a lot of energy. it can definitely absorb more energy than this green one, this tall one here. And so a lot of the time when we talk about materials, sometimes we think of toughness and strength as the same thing. They're not. Toughness is the ability to absorb energy, basically how much area under the curve we can get. Ductility is a material's ability to stretch or bend under loading. So a ductile material means that we have a larger strain. We go further on this x-axis here. But we want to be careful here. Just because this material, this green one here, doesn't go very far, we could still say that it is ductile compared to something else. Let me draw one more on here. I know we're getting a whole bunch of these on here. But let's say I have a material that does this, and it breaks there. This green one is more ductile than this other one that I put on here. A lot of these terms are going to be either comparative, or what they're going to do is they're going to be ductile for the purpose which we need to use them for. If I have a concrete that's ductile, a ductile concrete, it's still probably going to be pretty brittle compared to a lot of other types of materials. But as far as concrete goes, maybe it's somewhat flexible. Still probably not flexible at all, again, compared to most materials. Flexibility is similar to ductility. Flexibility is the ability to return to its original shape. So it's kind of like ductility, but it's in this plastic region. So how much can I deform a material? How much energy can I put into the material and have it bend back and have it go back to its original shape? Brittle is the opposite of ductility. It's the inability to deform before fracture. And so again, I can say that this red curve, the first one that I drew here, that is a more brittle material than the blue one. Now, it doesn't mean that it is brittle always, because if I'm comparing it to this green curve that I did, then it's definitely not brittle. Again, these are dependent on what we're looking at. But brittle in general means that it is going to fracture sooner than deform. Lastly, hardness is our resistance to deform, and often this is for indentation or scratch purposes. Again, kind of sounds similar to brittle. It has to do somewhat with strength as well, but it means that it's going to try not to deform. Wanted to touch on shear stress just really quick. This is different than normal stress. So we've been talking pretty much about normal stress this entire time. But shear stress is stress that's not normal to the applied load. And so if I were to take this picture here and I would apply a load that, let's say, was uneven, so I'd push this top part and bottom part opposite each other, I'd have this area in the middle, and instead of this area stretching, it would kind of shift. Maybe there'd be a little bit of twisting or something here. That is our shear stress. And we get a picture that's very, very similar when I plot this. I could plot my shear stress and my shear strain, and I'd get a picture that looked something like this. The values would be slightly different. It would be measuring my shear stresses and strains rather than my normal stresses and strains, but I'm still going to get things that are similar. Instead of a Young's modulus that we have a capital E for, what we have is we have the modulus of rigidity that we use a capital G for, and we have a equation to basically jump between those two. It uses Young's modulus and it uses Poisson's ratio, and Poisson's ratio is the ratio of our transverse strain over our axial strain, and from what I remember there, that should be negative. Our axial strain would be how much it changes as we pull on it with that pull in our normal area, and our transverse is kind of how that width changes. So as I have our material here, our axial strain would be how much we change along our axis that we're pulling it along, and our transverse strain would be how the width changes as we pull it. Just because I don't think I'd written it out yet completely, I wrote our relationship using Young's modulus here. Our stress equals Young's modulus times strain. Once we get out of our linear region, we're in our strain hardening region. This is not linear. It has the form of a power function, and so I wrote that relationship here, where K is our strength coefficient and N is our strain hardening exponent or our strain hardening index. Besides our tensile tests, we do have other ones. We have our compression test, where I compress a material instead of pull it apart. I didn't put it on here, but we do have some other tests. We do have bend tests. There are torsion tests where we twist materials. We do have hardness testing, where I can scratch a material or I can try to indent a material and leave an impression on that material. And I can impact a material. I can hit it with a whole lot of energy, try to break something with a big, heavy mass. Again, in class, we can talk about these. We do have some labs in other classes where we go through and we do a lot of these other testings. But again, this is just our overview. Really quickly, I want to touch on two other things. We'll talk more about these in class, but I just want to touch on them so that you guys can begin thinking about them. Some long-term mechanical properties, properties that take a long time to exhibit. We have fatigue and we have creep. Fatigue is weakening of a material due to cyclic loading. This means that I'm going to load, unload, load, unload, load, unload. I'm going to repeat that loading over time. So in class, sometimes I do this. Imagine a paper clip. We're going to straighten it out. Then I'm going to bend it one way, maybe at about 90 degrees. Then I'm going to bend it the other way. Then I'm going to bend it back. Then I'm going to bend it. And I'm going to keep bending it back and forth. The first time you do it, it doesn't break. The second time you do it, it doesn't break. But as you keep doing it, it will eventually break. But yet, it didn't break the first time, so how come it eventually broke? And the idea is it broke because of fatigue. I repeated an action over and over. I applied a load to the material multiple times, and it could only withstand that load a certain number of times, even if individually each bend wasn't enough to break the material. This can happen in both the plastic and elastic regions. The mechanisms for it are microscopic cracks begin to form at stress concentrations or stress razors. Spots where the stresses in the material are a little bit stronger, and again, that can happen in strain hardening. But as I do have some stress inside my material at different spots, it's going to form these cracks, and as I continue to apply and reapply this load, the crack will slowly grow until it reaches a critical size. Then it will propagate quickly, and then we have failure. Fatigue life is the number of cycles something can take until failure. For a lot of materials, it's pretty high. Thousands or millions or even billions of cycles until a material fails. A fatigue limit, fatigue strength, or endurance limit is the stress level below where, I really wrote that one long, it's the stress level below where an infinite number of loading cycles can be applied without fatigue. So in other words, I could load and unload an infinite amount of times and my material will never break. I never reach this kind of this critical amount where the material will eventually fail. If I have what's called a low cycle fatigue material, I basically say that I do this in the plastic region. I deform this material into the plastic region, into that strain hardening region. It's called low cycle because I'm going to get fewer loading cycles out of it before it fails. I can have a high cycle material, a material that gets into a lot of cycles before it fails, tens of thousands, hundreds of thousands, millions, billions, whatever it might be. And this is where I repeat the deformation, but in the elastic region. I never even get to my yield point but yet my material will still fail. So I'm just going to sketch this out really quick. We have what's called an SN curve, S for our loading and N for the number of cycles. Oops. I keep hitting the wrong button. All right, here we go. I'm going to draw this out. We have our load on the y-axis, or our stress that we're applying, and I'm going to get my number of cycles. This is my S, this is my N, our SN curve. So what I'm going to do is I'm going to have some value here. If I just have one cycle until it breaks, that's not really one cycle, that's a tensile test, or it's a torsion test, or it's whatever we're doing with it. And what I'm going to do is I'm going to have 1 point. So every single time a material fails, I get a point. What I'm going to do is I'm going to say, all right, that's my maximum stress my material can take. I'm going to lower it slightly, and I'm going to say, all right, so I'm going to lower my stress. I'm going to do it multiple times, and eventually it's going to break, and let's say that is at 10. And I'm going to lower that slightly, and let's say that's at 100. Lower that slightly. I'm at 1,000. We normally use some type of logarithmic scale down here because these numbers get big really, really quickly. But I'm going to end up with a curve that does something like this. This is going to be my low cycle region. I'm applying a pretty high load. It's in my plastic region. It's low cycle. I'm going to get to a point, and sometimes there is a slope change here that we can physically see. Maybe there is, maybe there isn't. Then I'm going to get to a point here where I get into my high cycles. My numbers get really, really big. Maybe this is 10,000 to a billion. It's my high cycle loading. Something that can take a whole lot of loads before it fails. And some materials will eventually flatten out, and this is our fatigue limit. Some materials don't have a fatigue limit. Some materials do. And so again, possibly at some stress, I could have an infinite number of cycles and my material will never break. There's a couple other points on here that I want to point out really quickly. If I'm above this curve anywhere, so anywhere above this curve, this is what we call our fatigue failure zone. That's our bad zone. It's going to fail. We don't want to be there. If I'm anywhere underneath my curve, this is called our safe zone. I am safe to have my material have any number one of these stresses with its correlating number of cycles. So that was really quick. There are a lot of cool examples that we could talk about. This one real quick, I want to talk about creep. Creep is similar to strain, or sorry, it's similar to fatigue, except for it's due to a constant load, not cycling our load. So the idea here instead would be I have a bookshelf, I have some type of shelving, I put a bunch of stuff on it. It's not heavy enough to break it right away, but after a month, maybe it starts sagging a little bit. Maybe after a year, it's sagging a little bit more. After 10 years, it's sagging even more, and at some point, the shelf's going to break. I never, unloaded the shelf, loaded it back up, unloaded, loaded back up. I'm not going through these cycles. And whatever I put on the shelf wasn't enough to break it just in its current state. I never reached that stress, that load that was going to break it just with one cycle. But the constant load that never went away is going to, again, exploit stress concentrations. There's going to always be some movement inside the material, and these small cracks will eventually form, and they will propagate until we have failure. And so some things to possibly think about and things that we could discuss in class would be the wing of a plane. If a plane wing is, if a plane is on the ground, the wings are going to sag and they're going to just sit there. And if the plane sits there for a really, really long time, we might have some creep involved because you just have this weight of this wing that just is hanging there. But when a plane is in the air and there's some turbulence and there's lots of air pressure and there's lots of movement, the plane wing is going to flex and it's going to unflex, and then we would have an instance where maybe we'd have to get into fatigue, and we'd see what's happening as the wing is going to be compressing and uncompressing at different spots. We can think of a wheel. So you have a car, and when you drive it a lot, there's always going to be a point where the wheel is in compression. I'm going to exaggerate it here. This is the wheel of my car, and because my car weighs so much, my wheel compresses and kind of becomes an oval shape. And if I kind of draw on my car and say, all right, that's the point of my car, the wheel that is touching the ground, as I rotate my wheel, it's going to be compressed still, except for not the part that it used to be touching the ground. And as I continue to rotate my wheel, the part that was in compression is now in tension, or vice versa, and each spot in my wheel is going to fatigue as I drive it. Likely, or just not likely, but with creep, if my car just sits on the ground and I don't drive it, and it sits there for a year or 2 or 3, my wheel is going to be in a creep type situation. And one that might be an interesting one to talk about because of possible safety issues, and also because it's kind of cool to look at, would be possibly things like a glass bridge. They have these bridges that are glass. You can walk over them and you can look down where you're walking. You can look at a canyon or off a cliff as you walk over this. And things that we have to possibly think about here would be things like creep or fatigue, because the glass itself that they're going to use is going to be glass that's very, very strong. And so we know that it's not going to break because of one person stepping on it. But with lots of people stepping on it, possibly with people dropping things or having little rocks on their shoes or dropping their phones or whatnot, you're going to get some surface imperfections. And then the constant flexing of people walking on it and moving on it, it's going to start wearing down over time. And we need to know how many cycles of a certain load make it safe for us to be able to use this bridge. So those are just some things we could start thinking about. Really quick overview, even though it took some time, but there's just a lot to go over. And we'll just continue talking about this in class as well.